This week we'll look at how to solve linear simultaneous equations. There are a lot of applications in engineering where you have to do so. So let's start with some basics here. And what is a linear equation? Well, let's say we've got three unknowns. We're calling them x, y, and z. As long as our equation only has linear terms of those variables, that is, the variables multiplied by a constant and other constants, then that's a linear equation. So any nonlinear equations would have terms like, again, like x squared, cosine, e to the x, all of those. So all those are nonlinear, and we'll look at some methods for solving those a little bit later on. But for now, we're going to concentrate only on linear equations. And as I said, there's a lot of applications in engineering that do result in a series of linear equations to be solved. So first of all, we have to write these equations in matrix form. So here's a linear equation with x, y, and z. And from what we learned about multiplying matrices, here's how we can write that equation. We can take the coefficients, 3, 4, and minus 7, put them into a row matrix, multiply them by the column matrix of unknowns, and we have our answer, the scalar that's on the right. So 1 by 3 times a 3 by 1, of course, gives us the scalar 1 by 1. But now let's add another equation. So our second equation is just shown here. And we'll do that. We'll just add on to the matrices we have before to the matrix equation by putting the coefficients of the second equation as the second row of the first matrix. Again, those get multiplied by x, y, and z. And the result of that is the constant 40 on the right-hand side. And so now we have a 2 by 3 times that column matrix, still a 3 by 1. But now our answer is going to be a column matrix 2 by 1. And do one more equation. X plus 5y equals 33. So of course there's no coefficient of z on there, so we put in a 0 for the z spot. So we would read that as 1 times x plus 5 times y is equal to 33. So now we have a 3 by 3 matrix on the left, a column matrix of our unknowns, and a column matrix of the same size as the unknowns as the constant matrix on the right. So just kind of review things you know from algebra. If you have more unknowns than you have equations, you're not going to be able to find a solution. If you have more equations than you have unknowns, then some of those must be redundant, and you don't need all of them. So what we're looking for is where you have exactly the same number of equations and unknowns. In that case, we could have a unique solution, and we'll see the conditions for that in just a little bit. But in that case, the coefficient matrix, that matrix on the left, is going to be square. So again, we would write this shorthand as saying a times x is equal to c. If we say that, then a is that square coefficient matrix, gets multiplied by the matrix of unknown values, which is a column matrix, and that multiplication results in the matrix of constants, which is a column matrix. Now, let's show an example here of how we would solve simultaneous equations. Algebraically, we'll just use 2, make it a little simpler. And what we're looking for are values of x and y that will satisfy both of those equations. In other words, simultaneously satisfy the equations. So we'll do this by substitution. I'll skip through this pretty fast, but obviously you write the second equation in terms of y, substitute that into the first, and we solve for x, and we find that x is minus 5 and y is 8. So there's our solution. X minus 5, y is 8. With only 2 variables, it's easy to draw a graph. Each equation defines a line on an xy graph. And in this case, here are the 2 equations of those lines in the form y equals mx plus b. And if we graph those, we'll see that they do cross at that one location. And if we zoom in a little bit, we can see that that location is indeed x minus 5 and y equals to 8. So that is our solution. Now, to solve these with matrices, first of all, we would invert the coefficient matrix and multiply both sides. So if that multiplication is on the far left of the left-hand side, it's got to be on the far left of the right-hand side as well. In other words, you can't switch the order of these. But now, if you look at that first term, you have inverse of A times A, and so you know that's equal to the identity matrix. And the identity matrix times the matrix of unknowns, X, is going to just give you X. And so there's your solution. To find the unknowns, you take the inverse of the coefficient matrix, multiply by the constant matrix. So let's take a look at those two equations, and we know how we can do the inverse of the matrix by hand with a 2 by 2. First of all, we have to write them in matrix form. So the first equation, 2x plus 3y is equal to 14. The second one is minus 4 times x plus 1 times y is equal to 28. To invert that, we first would find the determinant, which is easy to do for a 2 by 2. It's equal to 14. And then to find the inverse, we multiply 1 over the determinant. We switch A11 and A22. We change the signs of the off diagonals and multiply, and so there is the inverse of the A matrix. And now when we multiply that by the constant matrix, we do get the answer minus 5 and 8. Now in MATLAB, it's easy enough to do. Just put in the A matrix first. Remember, the semicolon separates the rows. C is a column matrix, so we do put that in with the semicolon as well. And take the inverse of A, multiply by C, and we get the answer minus 5 and 8. Now, the second equation is a little different here, and if we try to run this in MATLAB, we get a warning. It says the matrix is singular to working position, and our X comes out to be infinite. To think about what this means, if we try to solve this with substitution, and again I'll go through these pretty quickly, but what you come up with is 0. The x's cancel each other out, and 0 is equal to 0. So in other words, any value of x is going to satisfy this equation. And if I graph these, you'll see that the two equations are actually identical, so they form the same line, and so any point along the line will satisfy the two equations. And if you look at those equations carefully again, you'll see that the second equation is simply the first equation multiplied by a constant, which again is just the same equation. So in this case, there's an infinite number of solutions. But now if I change that just a little bit, all I've done is in the second equation I've changed the 24 to 28 and try to solve that by substitution. Well, first of all, the MATLAB gives us exactly the same warning. But if I try to do this with substitution, what I'll come up with is that 2 equals 0. Well, no value of x is going to satisfy that. So in this case, there is no solution. And if I graph those two equations, you'll see that they're just offset. They're parallel lines. They never intersect, so there is no solution here. So again, both of those give you the same warning or error in MATLAB, but what it means is there's either no solution or there's an infinite number of solutions. And what we're looking for is a series of equations that gives us one unique solution. And by the way, in both those cases, you would see that the determinant of that coefficient matrix is equal to 0. So to summarize here, if that determinant of the coefficient matrix is equal to a non-zero value, we're going to be able to invert that. There will be a solution, and that solution to these linear simultaneous equations is the only solution. It is unique. And if the inverse does not exist, then it either means that there are no solutions or that there are an infinite number of solutions. And with that, we'll look a little bit more about solving these equations in MATLAB and Excel in the next video.